Good morning, everyone. How are you? How's everybody doing? So it's already 11 o'clock. I think we should get started, Ashish, without
Yeah,
wasting
sure.
any time. Yeah. Cool.
Sure, makes sense. Okay. All right, I'll take it over from you. So just let me quickly share my screen. Okay. I hope you can see it now.
Yeah.
All right. So once again, a very good morning to everyone who is attending this, and also thank you for joining me here. As you know, this is the second part of my workshop for deep learning with PyTorch. Before I go forward with today's agenda, quick question, Ritu. Do you want to do those Q&As as you discussed yesterday? Or should we just go ahead with today's agenda and cover it at the end?
I think let's start with the session now for now, and
Okay,
then we'll do the Q&A after the session, or maybe
sure,
middle
sure.
of the session.
All
Okay.
right. Yeah, okay. So, all right. So then we can get started. So just a quick refresher on what we did yesterday, right? So we worked mostly on image data. We built a couple of image classification models yesterday, and we worked on convolutional neural networks mostly. I want to switch tracks a little bit, and I want to take you to a slightly different class of models. So I am talking about sequence modeling. I'm talking about recurrent models. And instead of working with images, so first up, I want to have a quick exercise with you on textual data. So perform this task of text classification using what we call the recurrent neural networks. So this will cover both the recurrent kind of models, and also we will see how we should be working with textual data. Uh, that's the goal of the current exercise. And at the second half of today's workshop, I will end basically my presentations with walking you through a real AI app, a really cool AI app, which you can classify as, artistic AI or generative modeling, let's say. So the name of the application is Neural Style Transfer, and I will try to walk you through the different steps of how to make such an AI app, and it can give you a lot of ideas around generative modeling and artistic AI. And as we just mentioned, towards the end, we will keep some time for questions and answers, both for today's session and if you have some questions related to yesterday's sessions as well. So with that, we can get started with our first exercise, which is around text classification with RNN, recurrent neural networks. So on a high level, what are we going to do next? I guess you might have heard about IMDb. It's the Internet Movie Database. It contains reviews of all the different movies that exists internationally. So this is a basically textual dataset because people write reviews in the form of text. What we are going to do is we are going to pull a lot of those reviews from IMDb's website, and then we are going to do a text classification task, which is called sentiment detection. So movie reviews can either be positive or negative, largely speaking. So we will try to train a model which can take these texts, these reviews, and predict whether this is sounding like a positive review or a negative review. So with that, let's go through the different steps of this exercise. And for those who were following yesterday as well, they will be familiar with this flow by now, that we go through the different aspects, starting with the data set itself. So first up, I'm going to show you how we load this data set, how we pre-process this textual data into numbers, because machine learning models will not understand natural text, but they will understand numbers. So I will show you how we can do that in various steps. And once we have the numbers or the NumPy arrays, we convert those NumPy arrays into tensors because PyTorch understands the language of tensors. And before we wrap up this section, we also visualize a few samples of our dataset to understand what we have done, starting from the reviews in the form of text to numbers. So I'm going to walk you through the different steps now. Once again, starting from the very beginning, I have to import some libraries because we are working with Python. So import OS is straightforward to load files and stuff. Time is to, you know, time the different steps of our whole exercise. NumPy is for all the mathematical operations. TQDM is a library which we use to, you know, set the timer for or track the time for different kind of loops. This is a string is a specific text related library which contains this attribute called punctuation. So we want the list of all punctuations. This will be helpful for pre-processing our text to get rid of punctuations. You will see soon. Then we need counter because at some point we want to keep track of the count of the words that exist in the reviews. Matplotlib is for plotting. And then we come to all the PyTorch related dependencies. So we have seen this yesterday as well. But once again, Torch is the name of the main library. NN submodule contains all the things specific to the neural network layers. Optim contains everything about optimizers such as SGD, Adam, and so on. And then we also use something called the torch.utils.data. This helps us to convert whatever we have done with our data locally into the PyTorch data loader and the PyTorch data set. And we will again see all of these libraries being used in the next steps. If you are using GPU, this step of setting up the device might also be helpful. But for now, in this demo, I'm going to use a MacBook which contains no GPUs, only CPUs. And finally, I told this yesterday as well. This is an underrated step, but we should always set the manual seed of any of these experiments so that we can reproduce the results across different runs. So I'm going to run this now, which hopefully should run. The next step, as we mentioned earlier, we are going to focus on the data set, right? So I have added instructions here to download the data set. There is a zip file which you can unload and you can copy over this folder here, and it contains everything that you need, the test and the training subfolders. But that is done for us right now. So we already have that folder here. In this loop, what I am doing is I am going through all the train folder and the different subfolders between the different text files inside the train folder, and I am gathering all the reviews and the respective labels in my two lists, review list and label list. I will show this to you how this looks like in the end, but essentially you will see that I have 12,500 such files to go through for both positive and negative. So we have basically a total of 25,000 reviews. 12,500 are positive reviews and 12,500 are negative reviews, as you will see here. Now, just to examine an example, this is one of those reviews written in plain text form. So for a movie that gets no respect, there sure are a lot of memorable quotes listed for this gem. Just by reading this, you know that this is more like a positive review. So we can check. And yes, the equivalent label for this review is indeed positive. So this is just to examine that the data set looks okay to me. Now, as I mentioned, we can't, machine learning models can't work with text. We need to convert these to numbers. So the next few steps will be around converting this text into numbers. Let's go through those steps. As I mentioned, the punctuation is a list of all the punctuation marks in these kind of reviews. And we want to remove those because they are not highly significant for the machine learning models understanding. So you will see that is one of the first steps we do here. We remove the punctuations essentially in this step, and we lowercase the entire review text because yeah, the machine learning model does not care about wherever you have the capital letters. We just want to reduce it into standardized form. Next, we basically, if you notice in these two steps, what we are doing is we are taking all the 25,000 reviews and we are putting them all together in one big sentence. So that's this line. And then in that one huge sentence, we are splitting all the words. Basically, we are trying to see the counts of individual words across the entire reviews database, which is done in this step. So if I run this, as you will see, we are trying to remove the punctuations in this loop, and then we do the word count, and we sort the count with the most popular or the most common words at the top. and then we view the top 10 such popular words. As you may expect in English, these kind of articles like the, a, or like conjunctions such as and appear at the top, and this is expected, right? So we just sort them on the basis of their popularity with their word counts, right? And then the next step, which is to convert these words into tokens, is basically to assign them their index based on the popularity. So the is the most popular word, so we assign the index 1, and gets 2, a gets 3, and so on. Like the entire list of words get their own, get their equivalent index. So now we have found a way to convert words into numbers. Okay, so that's step number 1. Now we can apply this to each of the reviews. So what we will do is we will take each review, and for each word within that review, we will basically convert them into these numbers. So let me run this and then I'll show you what happens here. So it goes through each review, it applies this vocabulary like the tokenization on each word, and then it adds back to this list of tokenized reviews. So what happens in the end is we get this reduced form of review. For, if you remember, like this was the original review with all the punctuations, all the upper cases. Now it is reduced with all the punctuations dropped and everything is lowercase, and then it is tokenized into numbers. So you can see that A is translated into 3 because that is what we decided the token for A will be. So this is our most important step here, which is to convert these set of words into set of numbers. Now it's going to be more easy for our model to understand this, but our task is not done yet. Remember, our labels are also POS and NEG, so positive and negative. We also need to convert them into numbers. So what we do is we convert positive into 1 and negative into 0, so that our labels are also numericalized. So you will see now that the first label, which we saw earlier was positive, is now 1.0. Okay, we are not done yet. Why? Because now another problem is different reviews come with different length of different number of words, right? Again, our machine learning models, we need to standardize how we present the information to the model. So because the number of layers and the parameters in the model are fixed, so the way to tackle that here is padding. Okay, so let's say let me first run this and I'll show you what comes from the output of this cell, and then I'll explain you backwards. So this is the histogram of the length of different reviews, meaning you can read this as a majority of reviews are smaller than 500 number of words. Okay, so based on this, I decide that, hey, a sequence length of 512 words, 512 because it's a power of 2, so just to be really convenient. So 512 words would be a good sequence length based on my population data. And then what I do is I apply this function of padding the reviews. What happens inside this function is essentially you need to know two things. If the actual review length is less than 512, we append zeros to the front of the review. So zero is a wildcard number. It's just a padding integer. And then if the if the review length is greater than 512, then we clip our review up until the 512th word. So those are the two things we do inside this function essentially. What happens because of this is now our data set is standardized for all reviews with a length of 512. So I will show you just in a bit how it looks like, but essentially, or maybe I can just show you one example already here. So So if we look at one of the reviews now, the first one, it is padded with a lot of zeros in the front, and then there are those words into tokens. So that's how our data now looks like. It is standardized into 512 sized vectors, sorry, length texts. So having done that, now we are reaching almost towards the end of the dataset formulation, where we do the train validation split. So that's very straightforward. We decide that 75% of data will be training. So we use that as a splitting factor, and we get our train X, which is all the reviews, and train Y, which is all the labels, and similarly validation and validation Y. Okay, from here we have gotten our data in NumPy arrays format, but as we mentioned before, machine learning models in PyTorch will not understand NumPy arrays, they need tensors. So for that, we need to convert them into our tensor dataset and data loader. These two steps are really important. I mean, this will be helpful for you even in general. Basically, this is one line to convert a NumPy array into a tensor dataset for PyTorch. So you can just do torch from NumPy train X. This converts the whole array into a tensor and provides similarly the Y as a second argument to the tensor dataset function, or the class rather, and then it casts this whole thing into a PyTorch dataset, and the exact similar step for validation dataset. Once you have that, we need ultimately a data loader to iterate on. If you followed in yesterday's session, it'll be really helpful if we have data loader objects, which is again a very simple step. From the trained data set, we add batch size, which I chose as 32, and with shuffling enabled, and we get the training and the validation data loaders, and we will use them shortly for our model training loop. Now, before I wrap up this subsection, we can visualize a few samples. So as I showed you already earlier, one batch of our data will now contain 32 reviews. Each review will be of length 512, and you can see how they roughly look like. They start with zeros because they are padded with zeros, and they end with some meaningful tokenized text, and their equivalent outputs are either ones or zeros, basically positive or negative, which is of size 32 because there are 32 reviews in one batch. Cool. We have done the first step now. We will move on to the actual RNN model itself. Okay. So in this, again, we have two steps. First is to define the model object, and then also to instantiate the model object. And then further on, we will use this instantiated object for training the model. So bear with me on this one, and I'll explain you everything one by one. So one initial thing I want to get really clear with is, so far, if I showed you, let me, okay, so when we did the tokenization of words into numbers, we came up with 121,364 different words in our data set, right? So when these numbers are fed to our model, we are not going to feed them as they are, but first we are going to one hot encode them into these many dimensions. Anyone who is familiar with one hot encoding and dimensionality, sorry, the curse of dimensionality, would know that these many dimensions as input will blow up the entire model, and therefore we need this first layer in this model called the embedding layer. Now, what is the role of this embedding layer? The embedding layer takes all of these blown up 121,000 different dimensions from the one hot encoding, which is the input dimension, as you will see here, and compresses this into 100 dimensional. In our case, we choose the embedding to be 100. So it basically compresses the entire representation into 100 dimensional representation, which we call as our embedding. So we want to reduce the dimensionality first, because to work with so many dimensions would be a nightmare. Your model would take like years to train. And so that's our first layer, to reduce the dimensionality of our input along this like number of, the one hot encoded dimension. Then we use, once we have reduced into a reasonable number of dimensions for each token, or each token for each word, then we use an RNN layer, which takes that much dimensional words as input, and then it provides a hidden dimension which is even smaller. So as you know, the goal is always to try to converge like more and more as we go further into the model. So the hidden dimension will contain 32 dimensions. This is the hidden state representation of the RNN model. And you can use multiple RNN layers one after the other, but for the sake of simplicity, I'm using one. You could use multiple. That would make the model training slower, although as well. Okay, once we have the hidden dimension defined for RNN layer, we can take, we will take actually the last RNN layer's output in the time dimension as the input to the fully connected layer, which converts this 32 dimensions into one number, which is going to be our prediction probability between 0 to 1, basically either positive or negative reviews. Now that is only the initialization of layers. Let me walk you through the forward pass of this model. Anyone who attended yesterday's workshop would be following that we also need to run this forward pass method. So the forward pass method is quite simple. We expect an input of size sequence length, which is 512, comma batch size, which is 32. So first up, we apply this sequence to the embedding layer, which reduces this from this dimensions to sequence length, which is 512, comma batch size 32, which is, and then comma embedding dimension, which is 100. So it goes from 121364 to 100. And then this is the most critical step of this exercise, where we run the RNN layer on the embedding. So what RNN layer does, and just a quick refresher for everyone, an RNN, a recurrent layer, basically takes the input X, right, which in our case is this embedding vector. It takes that input, and this input has several time sequences. So you can unroll this into a 512 steps of uh, this RNN layer. So each of these 512 words of the sentence goes through the RNN layer, and the right side arrow here is the output, and the H for each of these time sequences is the hidden state. Now, what we are interested in the end is the hidden state of the last sequence. So the entire review is 512 words, blah, 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 blah. And then in the end, whatever the final word is, we are interested in what the RNN cell outputs at the really last word after having seen all the previous words. Therefore, you will see what we do is we feed the hidden state, the hidden state minus one. Minus one represents the final sequence, final word of the sequence, and then everything, the full batch size, the full hidden dimension. So minus one, comma 32, and then comma 32. And then we already we of course want to squeeze this first dimension because we want to make it um, in the same dimensionality as the fully connected layer. So we feed it to a fully connected layer all the 32 reviews of that batch with size 32, and we expect this fully connected layer to provide us just one output out of this for all the 32 reviews in the batch. I hope that was this was like the best I could try to explain this in limited time. I assure you, if you spend enough time on this code, looking at it, you will also get it sooner than later. Anyways, once we have defined all the hyperparameters, which we did, we can instantiate the model here with RNN model. Now, besides the model itself, we need to choose the optimizer, which I choose as the Adam optimizer with all the RNN model parameters. And then we also need to define a loss function, which in this case, we have a binary classification task, positive or negative reviews. So I choose binary cross entropy as my loss function. And again, if you're using GPU devices, then you need to also place this model and the loss function on your GPU device. In my case, it really does not matter. So I have run this cell now. We are now ready to go to the next step. So if I quickly come to the presentation again, our next step would be to define our model training and model testing routine, because we have the model, we have the data. So now we are ready to do that. To be able to test the model, we also need this accuracy metric. So this is very straightforward. Given some predictions, given some ground truth, how do you compute the accuracy? It is supposed to be the amount of matches between the predictions and the labels divided by the total number of data set size, basically, right? So this is our accuracy I have defined. And we go to the training. routine. Okay, the training routine expects this RNN model object. It also expects the training data loader, and it expects what optimizer we are using and the loss function that we are using. We have defined all of these in the previous steps, so we are ready with what we want. Now, before we go inside the data set loop, like starting to, you know, loop through the entire batches of data set, we instantiate our loss and accuracy metrics with 0. And we set our model in training mode, which is we tell PyTorch, hey, we want to update the parameters of this model within this function. Okay. Now, within this loop, again, very similar to yesterday's discussion around model training loop, first we need to flush off all gradient from the previous epochs so that we have a fresh start. Then we run the forward pass through the model. Some people might ask, hey, why do you have a transpose here? This is something related to PyTorch's APIs for RNN models. We need to just make the dimensionalities match as expected by the model. So the way our sequence arrays are defined, it makes sense for them to be transposed to follow the convention that they are expected to be in the model. So we get the predictions, and then with the predictions and the label that we have already from the data, we can compute the the loss for this current batch of reviews and the accuracy. Once we have the loss, we can back propagate this loss to the network. We can update the parameters of this network, and at the same time, we can update our losses and accuracies for this current batch, add them to the global loss and global accuracy. And in the end, we return the normalized loss and accuracy across the dataset. That's the goal of the training routine. Validation routine, as you can see, is almost the same. The only difference is we don't set the model to training mode. We set the model to evaluation mode because we don't want to mess with the parameters of the model. We only want to evaluate the model. And so there is no back propagation or updating of parameters. Okay, so I'll run these, and we have defined this. And now I think we are ready to just run the model training loop. So what this really means is we need to define what number of epochs we want to train the model for. We then define what is our best validation loss so far. We start with infinity because we can only go better from there. And then we run this model training loop. In this training loop, we basically run the train and validation routines in every epoch. We record the time spent in these routines, and at every epoch, we check, have we seen the best validation loss so far? If yes, let's save the most recent model. Otherwise, let's go to the next epoch. So that's all we are doing here. I'm going to run this an accuracy metric not defined because we haven't run this one. So I'm going to run this here.
Sir, one
And
small question, please. Sarji,
sure,
I'm sorry disturbing you in between. Now
sure.
you says there is no backward propagation, only forward. So how do you differentiate one epoch equals backward plus forward propagation or only forward propagation?
So there is both backward and forward propagation in this. So in the training routine, which we are calling first in every epoch, there is this backward propagation, which makes sure that the model parameters are updated, right?
Okay, okay.
And then there is the validation, which only has the forward propagation.
Right, right.
Yep. So as I said, I will run this, but RNN models are even more complex than the usual feed forward or the CNN models. It is going to take some time. So again, in a cooking show fashion, I have run this from before. So I'll show you the logs for 10 epochs. And as you will notice that for each epoch, we record the losses, and you will notice the losses to go down, but more interestingly, the validation accuracy goes all the way from 20% roughly in the beginning to 67% towards the 10th epoch. Obviously, we need to train it for longer to get for higher number of epochs, but that's beyond the scope of this exercise. Now, we won't wait for the training to run here. So I can already move to the next and the final step of this exercise, which is once you have the train model with you, we can use again this train model to make predictions on real-time reviews and see how the model performs. So firstly, you can see that the model is saved here already from before, the rnn model.pt. And then we basically define a sentiment inference function. in which we set the model to evaluation mode. We take in the sentence, the review. We apply all the pre-processing steps that we did to our training data set, right? So first we make it all lowercase, we remove all the punctuations, we convert all the words into tokens, and then we apply the padding in the same fashion. Once we have done all of this, we convert our array into a tensor, and then we basically pass it through our model, the feed forward step, and get the sigmoid, basically the probability prediction probability from the model, and we return the probability. So I have run this for our some of our statements. So I began with something which is like clearly negative, and we saw that there is an output of 0.467, which is uh, somewhere in between but closer to zero. And then I begin adding like slight ambiguity to the review. Director tried too hard, but this film is bad. And so the review slightly goes up compared to the previous one, which is a good behavior. It means the model is tapping onto the actual sentiment. Now I go from negative all the way to positive. So I say decent movie, although could be shorter. This is not truly positive, but it is quite on the positive side when I say decent. So the sentiment probability goes up to 0.972, and now I go all the way in. So this film will be houseful for weeks. I haven't said good or bad specifically, but I have said houseful, which should refer to good. And so the model apparently picks that up and goes even higher in probability for the review. And finally, I really love the movie. Every part of it, it was amazing. And then it goes at the highest probability. So this just shows that the model has learned basically the correlation between the sequence of words when they refer to a positive review for a movie or when they refer to a negative review for a movie. A few notes before we conclude this exercise. You can feel free to change or like firstly train it for longer, as I always say, and also play around with the hyperparameters that we have used in this entire exercise. You can change these dimensions, you can use more layers for RNN, you can define a different set of sequence length for padding, and you will for sure perhaps get better results with some and get worse maybe if it's others. But this is an exercise, a fun exercise I would say, to both understand how textual data can be modeled with deep learning and also to use PyTorch for such a complete end-to-end exercise. So I think that is it from the current exercise. um, I could move on to the next one, but Ritu, just to check in with you quickly, do we want to run Q&As in between, or do should we go to the next exercise straight away? Ritu, if you can hear me.
Ashish, it will be better if we can take questions in between, because if we are stuck at
Okay,
some point, then subsequent like your sessions will not be like very much.
sure, sure. Sure.
I
Okay,
have
if
just
Ritu,
2 or 3 questions. You are okay with it?
okay, Ritu, are you okay with that? I think we don't have her right now. Okay.
Better
I
if
mean, we
I
can.
just ask
Yeah.
questions. Yeah.
Sure,
So,
sure, sure.
how do we decide that how many folks will be sufficient to train our model? How do we reach to that particular? I mean, how do we do the model evaluation in CNN and RNA? My point is like.
So, so when we are training the model itself, the validation set is your indication for whether you have reached optimal performance or not. So, for a binary classification task, if I have reached only an accuracy of 67.51%, it
Mhm.
means that I can do better, right? So I look at this training curve to understand. Let me tell you something here. So if you are familiar with the concept of overfitting, you can see that this particular model is actually overfitting because the training accuracy is
Mhm.
going all the way up to 95%, right? But the validation accuracy has struggled a bit. So it has gone up and then it is slightly oscillating. So this basically tells me that I should firstly apply some regularization maybe. I should maybe add more data, and then I should, once I have addressed the matter of overfitting, I should train it for longer. Maybe I should use some smaller learning rate because my validation accuracies are shooting up quickly but then just oscillating. So maybe using a smaller learning rate will help the model to gradually reach to that point of optimum. So it is a mix of various things. You need to basically, your starting point where to understand how the model is working is your learning curve, which is basically plotting these numbers. If you plot the training and the validation accuracies and the losses together, you will see how your model training is going. In this case, I will repeat, your training loss, okay, is going down from 0.6 to 0.132, but the validation loss is more or less fluctuating, which ideally is not a good sign. So you should think about addressing this, the overfitting problem, and then come up with more training exercises with different hyperparameter settings. Maybe you might want to reduce the parameters. So, oh, maybe embedding size of 100 is too much. So let's start with 50. Maybe hidden dimension of 32 is too much. Let's start with 16. Maybe this helps to keep the overfitting in check. So there are
Okay,
so many.
apart from this like training accuracy and validation accuracy, training measuring the
Mhm.
losses, what is there anything else like you have ROC curves kind of things are there in
Of
your
course, yeah, of course.
yeah? What are
So
the other parameters that we should go and check? I'm not asking you to do that. I just want you
sure,
to
sure, sure, sure.
give some names that we should check
Okay,
for
so for binary classification, there are accuracy is the most basic thing, but most often the thing that helps in industry the most is the precision recall trade-off. So the precision recall curve is one of the most important ways of looking at how your binary classifier is working. So in this case,
do we have the
sorry,
ROC curve also here in CNN RNN? Like,
yeah, it is independent of CNN RNN. It is more dependent on whether the task is binary classification or not. So you can use the area under curve for ROC curve, right? Um, these two are basically the ultimate tools for using as metrics for binary classification, right? But you can't use this straight away during the training of the model because it is difficult to track them as one number. If you track your losses, that is a more direct indicator of how your model is performing, because your model is optimized to reduce the loss straight away, like directly reduce the loss, not to directly increase the precision on recall. So these are more metrics, right? But what is like the objective function? So the most
Ashish,
popular one is, yes.
I'm so sorry, but my mic was not working for some reason. We
Mhm.
can take two more questions and then we can
Sure,
hop on to the next
sure,
exercise.
sure,
Okay?
sure, sure.
Okay.
So as I was saying, the objective function, which is what our optimizer are working to optimize on, so which is binary cross entropy in this case, this will be helpful for the model training part, right? So this is what we need to focus on during the training. Once you have trained your model, right, then you can use this to compare, let's say, models A, B, and C, or whatever. Like you have several models trained now and you want to compare them on the final metrics, like how will your model perform, then you can use these advanced metrics as well. So
so
I would say
it's
these are
the final step after we have done it. Like,
because the keyword is metrics versus objective function, or you can say loss function. Metrics are more to finally check the performance of the model on a test set with different from different angles. But the training time during the training time, we need to just look at whether the approach that you are taking, is it able to really reduce the loss or not. So that's the most important part there. Hence I recommend you to look at the learning curve, which is this loss function plotted along the epochs during the training time. And once you have the models, then you can use these metrics to compare, whether my model A is better or model B is better, because these numbers are then going to give you more detailed insights.
okay, just one more question. Like, yeah, as you see this training loss or the training accuracy, it's like fluctuating. Okay,
Hmm.
so if even if we are increasing the epochs, what is the
Hmm.
guarantee that it will stop fluctuating and will start giving us the more consistent result? Does it
Okay.
happen in?
Mhm. So
Does
here,
it
if you
happen
notice,
in this case? Yeah. Sorry.
sure, sure. So here, if you notice, the training loss is consistently going down, right? What is fluctuating is the validation loss. So it's going down, but then going back up. To me, this tells that this is a telltale sign of overfitting. So that is why I said maybe our model has a high learning rate, maybe. So let's go with that assumption. So in that case, in this optimizer, the default value is 0.01, which is what we left it as, right? So maybe this value is too high. So the training side is going smooth because that's our training data. But when this model is used to evaluate the validation set, we are seeing that, hey, I think this model is going down the wrong path to quickly learn stuff, but this stuff is not generalizable because the validation set is suffering. So maybe what I would do is I would reduce the learning rate. What will happen in this case, if you reduce the learning rate and increase the number of epochs from 10 to 100, then what happens is you let the model conservatively take the next step. So it's not going to just rush to some conclusion in one epoch. Like in one, think of a
Okay.
valley, think of mountains and valleys for your optimization, right? So it's like it's just trying to find the quickest downward path to go to the nearest valley with a high learning rate. If it is a small learning rate, then it is going to be more conservative in taking the next step and then look around. And in that case, hopefully this happens most of the time, that it becomes more generalizable, because in being conservative it is going to take the most reasonable step, as opposed to in the case of high learning rate when it's just going to jump to overfit the training set. So that's what I was referring to. Also, if you have a very strong model, the model is so strong that it can basically learn the entire training. By learn I mean memorize the entire training set, which is not
What?
good,
Yeah.
because we want it to learn the patterns within the data, not the
Mhm.
data itself.
Right.
Cool.
Yeah.
Okay,
So
I
Okay.
have a
Any
question.
other?
I
more
have a
number. Sorry. Openly, there was just one more. Less learning rate and more number of epochs is going to give us the more calibrated output, right?
More generalizable output.
Generalizable output. Okay,
Yeah.
thank you. That's it.
Yeah, my only question was around dimensions only. So you be reduce the dimensions from or like 121,000 to 100.
Uh-huh.
So like so these 120,000 by dimensions, you mean 121,000 different words, right? So
Yes.
these were different words which came across in different reviews. So those
Yes.
were all our dimensions. And now, but we reduce it to 100. So means we are like feeding only 100 at a time. That's how it's working. I
Yes.
mean,
Exactly.
that part was not clear. I mean, can you explain like how exactly
Sure.
RNN
Sure.
works?
Sure. 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 Let's say. Let's say. Let me quickly give an example. Right. So movie is good. Let's say we have a very simple definition of English, and only 4 words exist in that language of simple English. And so the reviews that are possible with this language is movie is good, movie is bad, right? So what happens is, because we have only 4 words in this language,
Right.
we can represent each of these words as numbers. So let's say I say that movie is 1, 2 is 2, good is 3, bad is 4, right? Now, when we feed this to the model as input, we are not going to feed them as 1, 2, 3, 4. Why? Because we don't want to give the model a sense of ordinality. Because 4 as a number is bigger than 3, 3 as a number is bigger than 2, but that is not our intention, because bad by no means is bigger than good, if you know what I mean. We don't want the model to think in that comparative way. So what we would do is we would convert these numbers into one hot encoding. So 1 would be written as, let's say, 1000. 2 would be written as, sorry, 0100. 3 would be written as 0010. 4 would be written as 0001. So now each word itself would be represented by a 4 sized vector. So our whole thing would become, like it would be a list of lists, right? So the dimensionality for, so this guy movie is bad, which is 1 comma 2 comma 4 would be written in like this form, this comma this. Now here it's manageable because our words are only 4, so each dimension is it's manageable. So 1 comma 2 comma 4 is going to be, let me make it super clear so that 1 comma 2 comma 4. So what's the size of this? The size of this is 3 comma 4, right? This numpy array.
Right.
This part is 4 because our words are only 4 here, right? But if our words are 1 to 1, whatever, 3, 4, 5, these many words, then the representation becomes blown away. Like every word has to be represented in so many different numbers. And for our model, imagine imagine the number of parameters our model will need to have to process this. That is why we try to funnel this into a 3 comma 100 representation. So what happens is each word is now going to have a embedding which tells us what this word is about, instead of giving us a flat 0 1, like one hot representation. So that's the goal from going from this to this in simple terms.
And then this embedding is a different kind of a matrix. That, I mean, how are we representing this embeddings?
So basically in this case, you are 100% right. So it's a 131 1 to 1 3 4 5 comma 100 sized
Mhm.
matrix which is learned independently. That's why we have a separate embedding layer. And this basically learns the translation of these kind of one hot representations into compressed 100 sized representation. So this happens before the RNN model, because then the RNN model receives this compressed representation. And I can assure you, if you train such a model, like if we were to pick the embeddings, we don't have time for this right now, but you would see that movie, um, or film, these kind of words in this data set would have a very similar looking vector. By similar looking, I mean if you took the difference of these vectors for these two words
Mhm.
and took the mean square error, you would see a very small value because they will be very close enough.
Okay.
And if you suddenly took the word animal, it will have a huge difference compared to these two. So this layer is trying to find representations for words from our data into a smaller dimension, so that we don't suffer from huge dimensionality problems. But
Mhm.
in this, at the same time, it ends up finding meaningful representations. So that's the whole thing.
Got it.
Now,
Thanks.
one question
Thank you.
from my side, Ashish. When there is a fantastic RNN model we do have, what is the main significance of moving from RNN to LSTM? Only just because of vanishing gradient problem, or other than that also?
That's the main problem with RNN. It just the plain RNN is not able to catch long sequences, because if you think about this, the step that happens here, the RNN layer, or let me show you in this. So firstly, I really strongly recommend to go through this post. This is like perhaps the best resource to understand
So you
RNN
told
LSTM.
plain RNN. What do you mean by?
Simple, like vanilla RNN, like the one you are seeing here right now.
Okay.
LSTM cells are more involved, where you have uh, so many things going inside, but I will not go into the details. I'll just tell you from the outside what happens is in an RNN, how the back propagation works. It goes from the last sequence, like last part of the sequence, all the way through the first element, right? This is called BPTT, back propagation through time. Okay. Now we have 512 steps in the sequence. So this back propagation happens through 512 steps.
512 or 100 RNN outputs?
No, we have our sequence length is 512, right? So if you
Okay.
remember in our exercise, sorry, so yeah, if you look at our length of each of these, which we also I think visualized at some point at the top, each of the input is 512 size sequence, and we pad it with zeros, right?
Okay.
So this is 512. Okay, now imagine when back propagation happens. If you remember how back propagation happens, we use the chain rule of differentiation. Rule of differentiation is basically product of differentials across different layers. But now we have 512 layers to take care of. If you have a value smaller than 1 And if you keep multiplying such small values 512 times, you know mathematically that you will go and reach to a very small value. Similarly, if you have value bigger than 1, and if you keep on multiplying that 512 times, you know that it will blow up to a huge value. So those are the vanishing and exploding gradients problem on a high level. LSTM was devised to address these kind of problems. It has its own regulation mechanism. So it does not allow the previous gradients to just blow up the next gradient. It has a mechanism internally to regulate, to again bring it back to a value between 0 and 1. So it, whenever you go through the different layers, the different cells of LSTM, it does not allow a huge value to keep blowing up or a very small value to keep diminishing in a high, on a high level.
Okay.
So that's why LSTMs were devised in the place of RNNs. But this was just to show you that even if they are not the most efficient models, they still work somewhat okay for a problem like this. So I think with this we should go to the next exercise now, just to keep track of time, and then we can, if you have more questions around this exercise, I promise you we can come back to this even after the second exercise. All right. So let's move on to the final exercise of this whole workshop, and I assure you this is going to be really interesting, and you will want to hopefully run this yourself. So neural style transfer, in a nutshell, firstly I am going to describe what this whole application is, and obviously we are going to go into the details and we will implement it using PyTorch. But firstly, what I'm going to do next is we are going to take two images. Okay, one image which we call the content image is going to have the actual content as the name says. So I have taken the example of an image of our great Taj Mahal. The second image is the style image. Style because this is more like an artistic painting, you know, like one of those Picasso's, like, you know, modern art paintings kind of thing. And what the goal of neural style transfer is to transfer the style of this artistic image into the content image to make it look as if someone drew, some artist drew the image of Taj Mahal, which you can see on the right hand side, is pretty much what is it looks like. And we are literally going to implement this in our exercise just next. But before we go there, I think I need to walk you through some concepts to really make you follow the exercise. So remember two keywords. Sorry, one is content and one is style. Okay, so first focusing on the content. How are we going to formulate some loss functions here? Because the model needs some motivation to learn, and we need to provide some objective function or loss function. So we will provide two loss functions, one for the content, the Taj Mahal image, and one for the style image, which is the artistic painting image. So the content loss goes as follows. We pass an image through a convolutional layer. The convolutional layer gives us several feature maps for the image with slightly reduced dimension, maybe because we are running convolutions without padding, let's say. So we get from a 3 by 3 image, let's say we get three feature maps of 2 by 2 each. This is all hypothetical. This is just a toy example. So once we have these three feature maps, what we do is we flatten each of them individually into one dimensional vector. So this 1 2 2 2 becomes 1 2 2 2, 2 3 1 2 becomes 2 3 1 2, and 1 1 1 1 becomes 1 1 1 1. And we concatenate them all like horizontally, place them as a reduced 2D matrix representation for the entire image. This is just a compressed representation for the original image, right? So we do this for what we want to generate, our personal like generated image, and we do the same for our actual Taj Mahal's image, so the expectation, right? And then we take these two and get the pixel wise squared sum loss. What is that? So pixel wise meaning for each pixel we do the difference and then we square the difference. So 1 minus 1 is 0, and then we square it, so 0 square. 2 minus 1 is 1, 1 squared. 2 minus 2 is 0, 0 squared, and so on. And then we add all of them together, which gives us the pixel-wise squared summed loss. And we call this as the content loss. So just bear this in mind because this will come in handy when we run through the exercise. As I told you, there is one more loss, which is to motivate the model to learn the style aspect, not just the content, but the style aspect as well. So here we take the artistic painting. In a very similar fashion, we run the image through the convolutional layer. We get the feature maps. We convert them into this reduced 2D representation. The only difference in this step versus the previous one is that instead of using this 2D representation straight away, we convert it into its equivalent gram matrix. Firstly, gram matrix is nothing special. We are only multiplying this matrix with its transpose, which gives us a square matrix. And this matrix is called the gram matrix. So 3 by 4 times 4 by 3, hence the 3 by 3 matrix. This is classic matrix multiplication. You will ask me why gram matrix. So gram matrices are really good, even in computer vision literature, to extract the textural components of an image. What we want from the style image is not its actual content, but we want its texture. So we this paper from neural style transfer basically proposed this idea that if we use the gram matrix to compute the loss, it will inject the style of the style image instead of the content into our resulting image. So once again, we run this entire flow for the image we will be generating, and we run this entire flow for the actual style image, and we take these two, we again compute the pixel wise squared sum loss, and this is what we call as our style loss. So those are the two important elements you should know: the content loss and the style loss. Once we have those two, how do we use them for our full neural style transfer application? So this is our overall architecture, right? This is again hypothetical. I'm going to take you through the actual one in a bit. So we have a few convolutional layers, and we have generated image at the start. So this is something that we want to generate as we go along. Key things for you to know here is, in traditional deep learning, we only have the loss function at the very end, and then we backpropagate the errors and we update the gradients to the model. In neural style transfer, something novel was defined, which is, hey, we can attach losses to different layers outputs. So if we have a content loss here, it means we will also compute the loss here and inject back the gradients. Sorry. And if we have a style loss here, we will also do the backpropagation from this path. Similarly, we will do a backpropagation from this path, from this path, from this path. This is to say, we want to assess the contribution of different convolutional layer outputs. So having a style loss here means this whole pathway will force this image to learn patterns from the fifth convolutional layer, from the third convolutional layer, and so on. So that's the idea behind adding the losses at different convolutional layers. The second novel feature of this mechanism is we are not going to update parameters of the model at all. What we are going to update is the pixels of this image, because that's what we want to do. We want to go from some initial image that we want to generate, and we want to reach to an artistic representation of Taj Mahal. So this is the image itself is going to be tuned and not the parameters of the model. Now, with all of that, having said that, I will walk you through the different steps of the exercise, and I hope it will become all clear as we go along and as we read in the code. So once again, we have to first go to our data set. This is again standard, the libraries that we import. We go to the data set, and first thing I have is a function to convert an image to a tensor. So I have chosen two images, and I'll show you them very quickly. So you can choose any image you want. This is too big. This is my content image as I showed you, and this is my style image. You can literally go and take any two images from the internet. for your own use case, but that's what I decided to choose. So I will be loading them one by one into this function. What this function does is, firstly, it shows us the images, but then it also applies the transformations, if you remember, on the images. It resizes these images to a fixed dimension of 128 by 128, and then it converts them to a tensor. So let me run the function for the two images that we have, and this should output both the images for us. Yes, so as you can see them, now we have these two images ready for us to be used. That's step number one. Step number two is, when I showed you that model as an example, you might be thinking, you will not change the model parameters, so how will you train the model? So guess what, I'm not going to train the model. I'm once again going to use a pre-trained model for a different task. So I hope you might have heard of the VGG19 model. It's one of those advanced models that came after AlexNet. VGG stands for the Oxford University's VGG group, Visual Geometry Group. And the 19 here is basically to tell that there are 16 convolutional layers and 3 linear layers in this model. So hence 16 plus 3, 19. What we are going to do is, we are going to load a pre-trained VGG model, and then we will perform some modification on this model. We will edit some parts of it to make it useful for our use case. So let's see what we are up to there. First thing is to load it using the torch vision.models API, right? And I set the pre-train to true so that I have all the parameters intact. As you will see, this model has this feature extraction part, which is all convolutional layers. And then it also has a classification part with linear layers. So 3 linear layers and 16 convolutional layers in total, as I mentioned before. We are not interested in the classification part because we are not interested in the linear part. We are only interested in the convolutional layers. So first thing is, we will only retain the feature extraction part of the model. Okay, and I can maybe keep showing you the model as we go along. So now we only have the convolutional layers, but we have a lot of them. Next thing is, I told you we are not going to touch the parameters of this model. So this command ensures that I am going to freeze all the model parameters. I am going to set this requires grad flag for every parameter of the model to false. This will ensure that no one can train this model anymore. This model can only be used for forward propagation. Next up, so this is the technicality related to the style transfer. This current model has max pooling layers in between. For anyone who I suppose you know how max pooling works. So if you think about how back propagation works with max pooling is a very it is an impulse based function, because it is either a 0 or a 1 straight away. So either you choose out of these 4 pixels, let's say you choose 1, so it's a 1 or 0 straight away. So there is a sharp gradient for max pool functions, which can cause discontinuities in gradient calculations. And for a use case as ours, where we want to change the pixel of our input image, we don't want such sharp deviations to happen because it can cause patches in the image. So we replace max pool with average pool, because average pool takes these 4 pixels and does not choose the one which is the maximum. It takes the average of these 4. So it becomes very easy to backpropagate gradients, because gradient is now linear, because the mean function is a linear function of the inputs, as opposed to max, which is not a linear function of the inputs. So we replace the max pooling with the average pooling layer, and you will notice that now in this 16 convolutional layer model, we only have average pooling everywhere. Okay, while doing this, I have also done a slightly smart thing, which is I have noted down all the convolutional layer indices. So I have noted down what is the index of each of my 16 convolutional layers. The first convolutional layer is at index 0, second one is at 2, 5, 7, and so on. As you can see, 0, 2, 5, 7, and so on. And you will soon understand why I did that. So which brings me to the next step, which is the most important step now. now when I showed you in the presentation, let me go back a little bit. We were using the 5 convolutional layers of the model uh, for computing some style losses and content losses. In the actual paper, they only use the first 5 convolutional layers. They don't need the full 16 convolutional layers, which is what I'm going to do next. I am going to follow what was done in the paper. So I have defined a dictionary. This is a configuration file, more or less. These are the indices of the convolutional layer, 1, 2, 3, 4, 5. And the values are S. They contain either S and or C. S means style loss and C means content loss. So this tells us that, hey, I want style loss attached to the first convolutional layer, to the second convolutional layer, to the third, to the fourth, and the fifth. And I also want the content loss attached to the fourth convolutional layer. So how do we implement this? Firstly, because now we know that we only need the first 5 convolutional layers, it means that we need only first, second, third, fourth, and fifth. So we need only our model up until here. So we go and trim our model, as you will see in this line, and then we retain that much of the model, and our model is like, we basically call this our neural style transfer model. So you will see this is literally what we do in that step.
Sorry,
So
but
in
can you tell me how did you check the relevancy of the layer? Can you tell me
how could you repeat your question, please?
how did you check the relevant layer? How do you decide the
Yeah, so
relevant layer?
this is totally based on the actual neural style transfer paper that they retain until the 5th layer. I mean, you could even um, experiment by using even more or even less. I would encourage that as a hyperparameter choice. If you want to add more convolutional layers or remove this last one, but this is, I'm just trying to follow what has been done in the original paper.
Okay.
Okay. Um, Once we have done all of that, we have basically reached to the point where we have converted a full-blown VGG19 model into a neural style transfer model of our choice. Okay. So with that step done, we can go on to the next one, which is we need to initialize, we need to define the gram matrix. If you remember, we need the gram matrix for the style loss. And you should be thinking, how do we start training this model? So we need to initialize a random image. We need to start somewhere. So our task is to generate an image like the artistic image, right? So we need to start somewhere. So I will first define the gram matrix. So it's very simple. You first get all of the dimensions from your input. You convert your input into that reduced 2D representation, if you remember I showed you, and then you just multiply your reduced 2D representation with its own transpose. This is torch dot matrix multiplication, by the way. And once you have your gram matrix, you divide it, because when you multiply your gram matrix with its own multiply your matrix with its own transpose, you are obviously going to blow up the numbers. Because of the way matrix multiplication works, it is going to add all the rows in itself. So this step is done to normalize the values so that it does not mathematically blow up. That's the gram matrix. And then the initialization of the random noise image. So let me run this, and we have two choices to go for the initial image. What I have done right now, I have literally just initialized a random noise image. So all of the pixels here are random. And what we are saying is, let's start with this and let's slowly go from here and start learning, like start tuning the pixels of this image to make it look like a bit of both, a bit of Taj Mahal, but also a bit of an artistic painting. We can either do this or we can start with the actual content image itself. We can try the latter one later, but let's go with this current initial image, which brings us to the actual main step of neural style transfer model training or fine tuning loop. So we will now do this whole loop where we run this input image through the model of 5 convolutional layers. We will compute the content style losses. We will backpropagate the gradients not to the parameters of the model, but to the pixel of our initial image. And we will see how epoch by epoch our image is changing. So which hopefully will make it clear to you the process. So let's start with that. You will see firstly a few hyperparameters. I have defined the number of epochs to 300. This is again a hyperparameter. You can change it. This is just a setting that I have chosen. We need some weights for these two kinds of losses, the style loss and the content loss, because there are two losses which you need to add up, and you can add them up straight away, or you can add weights to the individual losses and have a weighted sum. According to the paper, I use the weights as they have used. So they multiply 10 to the power 6 weight to the style loss and 1 to the content loss. I maintain a list of style and content losses so that I can track them later across the epochs. And then this is a very, very, very important step you should focus on. I use the Adam optimizer, right? But let me quickly show you in the previous exercise. Whenever we define the optimizer, we declare all the model parameters inside the optimizer because we want the optimizer to tune all of these model parameters. But in our current exercise, we are explicitly asking the model only to optimize the input image itself and nothing else. So we are setting the input image, which is a tensor, to trainable format, and then we are passing this as the input to our Adam optimizer. So this is the neat trick, and this is like basically the essence of this whole application, where we are asking the model to tune the pixels of the input image. Then we enter into the model training loop. We ensure that the input image pixel values are between 0 and 1, because this is important because our further steps are going to change these pixel values, but we don't want them to go out of bound. So we always clamp them between 0 and 1. Then anyone who followed yesterday's sessions knows that this step again to clear off the gradients, to initialize the loss both for style and for content at the beginning of the epoch to 0, and then we iterate through these layers that we have defined here from 1 to 5, and we check for each of these layers, do we need to compute the content loss and do we need to compute the style loss? If yes for the content loss, what we do is we first send the content image through the style transfer model. So I'll show you the equivalent of this in this diagram so that it's really clear to everyone. So this line here is basically sending the content image through the style transfer model up until that convolutional layer, because we are only dealing up until that layer until that time, right? So we get the expected target, which is this value. Then we similarly send our own noisy image, which we want to become, which we want to start look like an artistic image. We send it through the same part of the model, and we get the predicted representation. And then we compute this mean square error between these two, as you see, we mentioned before. And we call this the epoch content loss. For the style loss, we do similar stuff, but we use the style image first and pass it through the model to get the target, which is this value. Remember that there is a gram matrix to be computed on top of everything. And similarly, we do the same for our noisy image, compute the gram matrix and call it IP. So this is what we are talking about there. And then we again compute the mean square error in the form of epoch style loss. If you're confused about this part, like why are we having this up to con indices, so and so and so, this is because you have to remember that if you want to, let's say, compute this content loss, only this much is your model. You can't forward pass through all of these layers. You're only focusing on that much. And so that's why you are using from 0 to that convolutional layer index. Okay, once you have gone through all the 5 layers and have computed the epoch content loss, basically summed them up for each of those layers and also the style loss, finally you apply the weights for each of those and sum them up. So this is a weighted sum for the content and the style loss. And once you have defined the total loss for that one epoch, you back propagate that loss. And here the back propagate means you're going to update the input image pixels. Cool. So that's actually it. At every 50 epochs, I show the statistics for the model, but I also plot how our resulting image, the image that we have started with as this noise, how that starts to look like. So I'm going to run this now, and you will see in the form of progression across the epochs how your how basically this input image, which is just pure noise, starts to learn from your two like style and content images. It starts to learn both a little bit of this and a little bit of that. The content loss makes sure that it learns the actual content from the Taj Mahal image, and the style loss makes sure that it learns the kind of texture, or the kind of distribution of colors from the style image. So we can go back to our model learning, and once again, because this, I know that these things can take time, so I have the progression here. So you will see from a totally random noise, the 50th epoch result looks like this. So you will see that you can't see the Taj Mahal at all here, right? So it is still learning. Basically you have this style loss and you have the content loss. If we go from the epoch 50 to 100, you do start seeing something is emerging from the picture now more clearly, and the style loss as well as the content loss both are reducing, which is a good sign, which means the model is learning something. As we keep going further, the image starts getting more and more of the content in it, and the losses keep reducing. And by the end of the 300th epoch, we have something that looks like this with the following style and content losses. So that's basically, in a nutshell, that's where we go from a pure noise image to something that kind of looks like a grainy, wax kind of a picture of Taj Mahal. There is a whole lot of hyperparameters to play around with to have different kind of results. If you start with the content image instead of the, so let me quickly run through this. If you start from the content image instead of the noisy image, you will again have a different set of results. And maybe I can quickly run that. But while we go and check those results, I have one last thing to show, which is we can also monitor how the model training actually happened across the epochs. So for that, I have just plotted these style and content losses individually for the 300 epochs, and you can see that they have been constantly reducing, both of them, which again is a sign that our model is learning something. Also at around 300 epochs, you can see that it is starting to saturate, and that is why I chose to train it for 300 and not more than that. So yeah, so this one is still learning, the live notebook. And while the current one, the one I want to show you with the content loss initialization runs, I can take or start taking questions from here on.
My first request is actually to share these notebooks with us.
Yes, so Ritu, let's do this right after the workshop. I am going to share all the links. So basically, I have these on my GitHub, and I just need to discuss the commercials with Ritu. If Pact, my publisher, is okay for me to publish these, Ritu, I am happy to share these with you and for everyone who is here to be able to use them straight away.
Sure, thank you.
Yeah.
Hi, Ashish. I have a question. First of all, thank you so much for these wonderful sessions. Really, really helpful for us. I have a totally different question on your book. while it says mastering PyTorch, is it a prerequisite that we already know deep learning, or it also takes us through the deep learning concepts as well?
For sure, it does take you through the deep learning concepts. So the first chapter is called Overview of Deep Learning. Um, it has sections such as layers, activation functions, optimizers. It does a whole review of basically the literature. Um, I would say understanding a good understanding of machine learning concepts such as cross validation, overfitting, how optimization works. Those kind of things would be useful to have a good, healthy start or a good learning curve to the book. But deep learning in itself is not a prerequisite, because I think we do cover the fundamentals from the first chapter itself. But yeah, Python, basics of Python is important, and basics of machine learning, because the book does not go through to explain, for example, how overfitting works, or how bias and variance affect the model. So those kind of concepts would be useful to know from a different resource. But if you want to get a good understanding of deep learning and work on deep learning with PyTorch, I think the book has a good starting point with the overview of deep learning.
Yeah. Hi, Ashish, Bhaskara here. Thanks for the detailed session. This is regarding the metaverse that we are getting into in the future. So how we can apply this into AR, the VR world, no, these concepts. Can you brief out to me if you have any ideas?
Yeah, so multiple ways. One example is computer vision is that discipline of deep learning which deals with, it's not a discipline of deep learning, but it's a discipline in itself, which basically can make use of deep learning via processing images and videos, right? And metaverse, if you think about it, has a lot of visual elements to it. So you can apply all those, starting from image classification to image segmentation to tracking, um, video analysis. All kinds of such modeling can also be applied to a simulated environment, right? Even in the simulated environment, you can do all of those things. So I will give you a very small example about um, human body tracking. So such models like computer vision models can be used to track the human body movement, right? And one of the key challenges, or one of the key problems to solve in the metaverse scenario is if we can really track our physical movements accurately in the metaverse, for some applications such as playing games together, or whatnot. So that could be a good way of using your skills which you have here, and applying it to the virtual world, basically mapping your current physical version into the virtual world. Another example could be simply using generative AI, like this example, literally using this example to generate images in the virtual world or for the virtual world. So you could learn a avatar creation model, which could take someone's face and create different kinds of avatars based on different sentiments, for example, so that you don't need a person to spend hours on Photoshop or whatever tools that they use to create that avatar.
Yeah, that's what I
So
wanted. When I see your this thing simulation, sorry to interrupt. Yeah, that's what I was coming to, like avatar creations, and then those avatar creations can be applied with respect, including these concepts about deep learning. Then we
yeah,
can do better things. Yeah.
yeah, and that's actually a huge market, I would say. Like, you should get on with that project if you are eager, as soon as possible, because I'm pretty sure many are working on such projects to
Yeah.
generate NFTs, let's say, using AI. So yeah,
Yes. Thanks, Ashish.
no worries.
Ashish,
Hi,
can we
Ashish, this is
that
Aman.
session? Can we have some link to, like, I want to buy your book, so if YouTube will
Sure.
provide us that link.
Yeah, sure. I mean, in yesterday's presentation, I did mention about the book. Via Ritu, I can obviously provide the links and everything. So Ritu, if you are okay with communication there, or I can literally just use the chat right now. I mean, doesn't matter. I can even just give me 1 second.
Yeah.
Sure. So for those who were here yesterday, I was just going through a walkthrough of the book. and somewhere here there should be this link.
Is there any discount given for UpGrad students, learners?
So that is what I'm really that is why I'm saying I am calling Ritu's name so often, because I just want to make sure that if there are discounts, you guys should get it, right? Because has been a promotion of the book in this UpGrad's workshop. So I am assuming that there is a discount, and Ritu can confirm for you
Yeah.
people.
So Ashish, I will have to check this and then get back.
Okay. I have shared the link for in any case. This is a Amazon UK, but I am sure this will open for Amazon India as well. And once again, please check with Ritu. You might have some substantial discounts here, um, and please make sure that you get the discount. If not, like we can even arrange Ritu afterwards. I can speak with packed people, because if there are so many people interested in the book, I am sure that they will be happy to arrange for a discount or something.
Yeah, please share your LinkedIn profile so we can connect also.
Yes, please.
Sure. Okay, I will share all of that details along with the presentation and the code via Ritu, if that's fine.
Thank you.
All right.
Ashish,
Any
this
more
is Saman.
questions?
Actually, I have one question. See, you have shown the curve between the training and testing. Now, what we have studied so far, that wherever there is an elbow, because this is a like an elbow curve, wherever there is an elbow curve, this is the most optimization point. But you and the elbow curve is there where both the training and testing is trying to be meet aligning there. That will be at 101. But here you are saying that the optimization is at 300 epochs. So is it the optimization is reaching at 100 epochs or maybe or 300 epochs? Because the difference between the training and testing curve or the loss may be the increasing as we are going beyond 100.
Okay, I totally get your point. One quick clarification is that these two lines here are not training and testing. They are two different kinds of losses. You can think of both of them as training loss. And you know what? In a task like neural style transfer, it is actually quite difficult to formulate a testing loss, because you will need someone to tell you that, oh yeah, this looks good enough, this does not look good enough. So it is very difficult to evaluate these models quantitatively. You can just look at them and say, yeah, this looks good enough. So for this example, I'm not sure that I can explain you how the optimum point will be reached, because we don't have the testing loss. What I was mentioning about this like plateauing is basically to tell that after this point, I am not sure if this will go further down. So we are almost reaching the saturation of the training loss, which is the style and the content loss. Now, if we go to your question, I think it's more applicable to our discussion on the previous exercise, where we had this training loss and the validation loss. We don't have the curve here, but we can still visualize, mentally, that the training loss from the very beginning is always going down, right? It's always going down. But the validation loss first went down and then went up. So this is already a red flag. This already means that something is not very optimal about this model. So we need to go back and tune the model again. It is going down, going up, and then again going down, slightly going up, and in the end it is still at a level which is higher than the second epoch. So this tells me, so this is basically my analysis of learning curve, that if my training loss is always, the training loss is like this going down, but the validation is always like fluctuating at a constant level. In that case, I was saying we are not reaching the optimum level, and so we should slow down our learning, let the training loss decrease slowly, and let's see how the validation loss reacts to it. Which is to say, let's see if we train slowly, whether our model is actually going to learn the true patterns and not just memorize the training dataset.
Yeah, hi Ashish. The last question, Bhaskar here. Did you
Sure.
try any time with the graph neural networks on deep learning related this type of exercise with the graph neural networks?
Yes, I have worked with graph neural networks
GNN.
and graph convolutional, graph CNNs.
No, no, I was asking about GNN actually, not GCN. Yeah.
Okay,
Did
okay,
you have any example? That will be great if you can share GNN with GNN.
okay. It will be difficult to put all of that together in like the form of an answer for 5 minutes, but
No, I don't
essentially,
know. Maybe later also I can connect through LinkedIn and we can
yeah,
talk
sure,
about it.
sure. So in a nutshell, one thing to remember is we are talking about graphical data, right? So if you think about social networks, for example, and you're trying to model the connections between people, the edges, and so on, so the data needs to be modeled graphically, and you can think of again having a matrix representation, which can be in the form of edge
But I
representation
tried
either.
PyGeometric, no, there is a PyGeometric, no, sir. I think there is a library.
Yeah, exactly. I was going to mention it. So they
Sorry.
have this. I mean, I highly recommend before actually we sign off. I highly recommend to everyone to visit also this page, PyTorch/ecosystem. So this page maintains a list of all the, best libraries that can be worked together with PyTorch. And no matter what you're working on, if you're working on explainability, they have good libraries here. If you're working on quantum mechanics, they have good libraries here. They have basically a lot of like PyTorch. The amazing thing about PyTorch is a lot of development is happening around this library, and so you have these different kinds of very well maintained libraries which you can use together. So as you were mentioning, right, deep graph library, for example, is also another one which is made for precisely graph neural networks on top of PyTorch. So with few lines of code, you can just add this to your PyTorch models and it'll start working for you. So I really recommend for you to also go through this page and check for your own use case what you want to work on. You might get some amazing libraries here, and it can make your life a lot easier to just train your models in a few lines of code.
Thank you very much. Thank you.
Yeah, no
Ashish,
worries.
Yeah, Ashish,
Thanks, Ashish.
last question. Just how is it
Right.
different from like Keras? Like,
Hmm.
both the libraries are offering like, the same set of functions, right? I think yesterday's session and today's session. So,
Yeah.
I mean, which one, like from the usability perspective or from the coding perspective, this is better, is what we're saying, like PyTorch
Okay.
versus Keras.
Okay. I'll be honest. I don't think that one is like 100% superior to the other. I will tell you just historical context. So Keras was developed in conjunction with TensorFlow, and it also got acquired, and now it's a part of the TensorFlow library. So the key difference between TensorFlow and PyTorch has, in the first versions, has been that TensorFlow worked on this entire, passive execution. So you build an entire graph of the neural network, meaning the entire, from beginning to the last layer. You first build the entire thing, and you tell which activation functions are going to be run. It does not execute anything until the very end. Only when you actually train or run the model, then it goes back and does everything. PyTorch, on the other hand, is very Pythonic. And when I say the word Pythonic, Python as a language itself is an interpreter based language. So when I run something in Python, these lines are already executed as soon as I run them. So PyTorch also works in a similar fashion. When I build a model, like when I do these steps, or in the previous example, let me quickly go to the model building part. Sorry. So if I when I'm building the model itself, uh, where is the model? Yes, okay. So when I'm executing these lines, right? So in TensorFlow, you would just these would be just taken as symbolic references, and they would not be executed until you actually ran the model training, which we do here. But in PyTorch, as soon as I define my model, it's already existing as a model object. I can go and I can check, I can debug what's happening inside that model. So PyTorch, because of its Pythonic nature, became very friendly for user interface. It's very easy to debug. Okay. There is an ongoing discussion between PyTorch versus TensorFlow. I mean, Keras is again a branch of TensorFlow. So there is an ongoing discussion always around this.
What
Um,
about PyCaret, sir?
Sorry, could you repeat that?
PyCaret.
So again, if we are going to
PyCaret.
discuss about, yeah, if we are going to discuss about the different libraries, let me just finish about the PyTorch versus TensorFlow. So the key difference is PyTorch has the advantage, has had the head start of being used as an interpreter-based kind of format, which enabled people to use it for debugging and so on. TensorFlow 2.0 later caught up to this, right? So they also started doing this. But I think PyTorch has evolved a lot thanks to, again, its ecosystem of so many libraries. So personally, I tend to use PyTorch more because it gives me more features on a day-to-day basis. But I would not go so far as to say, even though I wrote a book on PyTorch, I'm not going to say that it is definitely better than Keras or TensorFlow. To each their own. But PyTorch definitely has all the things that you can expect from any deep learning library. So if you are going to start with some library, I would really recommend to start with PyTorch because it has a more strong ecosystem of contributors. It is being maintained by a company called Facebook or Meta right now. So there is a high chance that this will also survive in the long run. And if you want to use TensorFlow or you have been using TensorFlow, nothing stops you from doing that too. So that's totally up to you.
Thank you very much. I think that's as clear as it can be.
Thanks,
Thank you very much.
thanks Ashish for taking out all the questions and for
No
extending
worries.
the session as well. And we'll discuss about the links that we were discussing. I have already mailed you regarding the same. So
Okay.
yeah, thanks Ashish for joining in so early. I know it's early
No
from
worries.
your end at London. So
Yeah.
all right, thanks. Thank you for your
Thank you
time.
so much.
Thanks
Yeah,
everybody
thank
for
you so much
joining.
to thank you so much to everyone who attended, and I really hope this was helpful to you. Yeah, feel free to reach me out, and I will make sure from my end to share with you the presentation, the code, and also I will really appreciate if you buy the book and you read it and let me know how you find it. So
Sure.
Sure.
thank you once again.
Ashish, Ritu, I just want to check. So, how are you going to connect with us to share this code? I mean, you can send it to email or?
Yeah, I mean, we can mail you, we can, on the platform, you can comment, text, however it is comfortable, we will share it with you guys. Don't worry.
Okay. Thank you. Thanks,
All
Ashish.
right.
Thanks for the wonderful
Thanks
session.
everyone. Thank you. Thank you,
Okay,
Ritu.
bye-bye.
Bye.
Bye.